Hello friends, so today we are going to solve questions from the chapter Modern Physics, and we are going to solve from the year 1998. Total of 6 questions from the year 1999, 5 questions. So in totality we are going to solve 11 questions. So the first question, which was asked in the year 1998, and it states that nuclei of a radioactive element A are being produced at a constant rate of alpha. The element has a decay constant lambda. At time t is equal to 0, there are n0 nuclei of the element. So based on this, there are 2 questions. Part A, calculate the number of n nuclei of A at time t. And part B, if alpha is equal to 2 n0 times lambda, calculate the number of nuclei for A after 1 half life of A, and also limiting value of n as t tends to infinity. So we are given that we have to calculate the number of nuclei at any time t. Okay. So we start with part A. In part A, we can write the differential form of the, you can say, number of nuclei. So you can say differential form of number of nuclei, and this can be written as dn by dt will be equal to alpha minus lambda times n, and this is a linear differential equation. It's a linear differential equation, and its solution is given as solution is n of t is equal to n0 minus alpha by lambda multiplied by e raised to power minus lambda t plus alpha upon lambda. And this is the, you can say, the number of nuclei at any time t. And for part B, we are given that our alpha is equal to 2 lambda times n0, and we can substitute this into the general solution, and for that let us find out our alpha upon lambda, and alpha upon lambda will be equal to twice n0, and let us call this as equation number 1. So we can say from equation 1 we can write that n of t is equal to n0, alpha upon lambda is our twice n0, and e raised to power minus lambda t plus twice n naught. So we get this as our n of t is equal to minus n naught e raised to power minus lambda t plus twice n naught. And after one half-life, we can write the equation that our t half will be equal to natural log of 2 divided by lambda, and this can be written in the exponential form as e raised to power minus lambda t half is equal to 1 by 2. So therefore we substitute in this equation as e raised to power minus lambda t, and this gives us that n of t is equal to minus n naught and multiply by half plus twice n naught. So this gives us that n of t will be equal to, this comes as 4 minus 1 will be equal to 3 by 2 times n naught. And this was our part B first part, and second is a limiting value. So for limiting value, as t tends to infinity, our e raised to power minus lambda t tends to 0. So we get our n of infinity will be equal to 2 times n naught. So this was limiting value. Next question. It was also asked in the year 1998 and states that the electron in a hydrogen atom makes a transition from n1 to n2, where n1 and n2 are the principal quantum numbers of two states. Assume Bohr's model to be valid. The time period of the electron in the initial state is 8 times that of in the final state. The possible values of n1 and n2 are. So it can be single correct as well as the multi correct. And here we have to remember that time period of initial state is 8 times that final state. Okay, so we can write that the time period of initial state is our n1 will be equal to 8 times time period for final state. Okay, because transition is taking from the initial state n1 to a final state of n2. And it says that Bohr model is valid. So we can write that for Bohr model, we can write the time period relation it gives us that our for nth state time period is Tn, and it is proportional to cube of that state. And we are having two states, so accordingly we can divide this equation into two parts and find out the ratio. So we get a time period of n1 divided by time period of n2 will be equal to n1 upon n2, and this as whole cube. Okay. And Tn1 upon Tn2 is 8. So we can write this will be equal to our n1 upon n2 whole cube is equal to 8. So this gives us that our n1 is equal to 2 times n2. Okay. Now this is the basic relationship, and one over one we can put the various values and try to judge whether this relationship holds true or not. Okay. So option number A, it gives us that our n1 is 4 and n2 is 2. So our option A gives us that n1 is 4 and we have our n2 is equal to 2. So obviously from here we can say that our n1 is equal to 2 times n2. This relation holds true. Okay, so this relation is our true. Okay, so therefore option A is correct. Option A is correct. Similarly, we take option B, and option B gives us n1 8 and n2 2. n1 is 8 and n2 is 2. And for that, if we want that our n1 should be equal to ideally 2 times n2, and which is not true in this case. So this relationship is our false. So option B is incorrect. Option C gives us that n1 is our 8 and n2 is our 1. Similarly, n1 should be equal to 2 times n2, and which is also incorrect. So this option is also false. And finally we are left with D, and D gives us that our n1 is equal to 6 and n2 is equal to 3, and this gives us that n1 is equal to twice n2. So this option is true. So option D is correct. D is correct. And C is incorrect and D is correct. Otherwise also we can also find out the time ratio. Okay, that should be 8. Next question. It was asked in the year 1998, and it states that let Mp be the mass of proton, Mn be the mass of neutron, capital M1 the mass of 10 neon 20 nucleus, and M2 is the mass of 20 calcium 40 nucleus. Then we have to find out how the relationship between M1 and M2 holds. And for that we are going to consider our, you can say, about the energy and the mass relationship, how they are, or basically we can say binding energy. So we can say if in a nuclei the mass of the nucleus is always less than the mass of its constituent protons as well as neutrons due to binding energy. Okay, this relationship is always true, which is also called as a mass defect. Okay. So we can say that in nuclei the mass of nucleus is always less than the sum of masses of its constituents protons and neutrons. And in simpler terms, we can write that the delta m, the mass difference, will be equal to Z multiplied by mass of proton plus A minus Z, and we have this as mass of neutron minus mass of the nucleus. And so based on this, we can write that the total mass m will be less than our Z multiplied by mass of proton plus A minus Z, and we have this as mass of neutron. And so in terms of the given question, we can write that the mass per nucleon for the heavy nuclei is our 20 Ca40, is less than that of the lighter nuclei. So we can say the mass per nuclei for heavier nuclei, that is our 20 Ca40, is less than that for lighter nuclei. And in this case is our 10, 20. And we can just also find out their, because it is given in the ratio, so we can also compute their ratio and try to get the more exact option. So their approximate ratio our M1 is approximately equal to 20 multiplied by mass per nucleon and similarly we can write our M2 is approximately equal to our 40, and we have this as mass per nucleon. And obviously we know that the binding energy per nucleon increases, the mass per nucleon decreases. Okay, that is our, you can say that since binding energy per nucleon increases, the mass per nucleon decreases. Therefore, we can write that the ratio m2 upon m1 will be less than 40 divided by 20, which is equal to 2. So this gives us that our m2 upon m1 is less than 2. And this option number C is correct. So from here we can say that our option C is correct. So option C just rules out these two options. Option A cannot be correct and option B cannot be correct. But we are going to check about this option number D. And once again, because of the mass defect, as or in the simpler terms we can say also binding energy. So we can say due to binding energy, our M1 will be less than 10 times our MP plus Mn. So therefore option this D is also correct. Next question. It was asked in the year 1998 and states that the work function of its substance is 4 electron volt. The longest wavelength of light that can cause photoelectron emission from this substance is approximately. So here we are given as a work function and we have to find out the longest wavelength, that is a lambda max. And we know that the photoelectric emission is possible if the energy of incident photon is at least equal to the work function. You can say photoelectric emission is possible if energy of incident photon is at least equal to the work function. Or in terms of the formula, we can write that our energy is at least equal to work function, and which will be giving us hc upon lambda. And we have to find out the lambda max. So you can see our lambda max will be equal to, we have this hc upon work function, and product of h and c in terms of our electron volt is 1240, and work function is also given as 4 electron volt. therefore we get that our lambda max will be equal to 310 nanometer. So option number C is correct. Next question. It states that the half-life of 31I is 8 days. Given a sample of 131I at a time t is equal to 0, we can assert that. So we have to find out that half-life is given 8. So we are basically, it is asking about the nature of radioactive decay. And where we have to remember that radioactive decay takes using under, or we can say through two ways. One is the random and other one is the spontaneous. So we can say that radioactive decay is first is our random and second one is our spontaneous. But both these processes are governed by probability. Governed by probability. So it means for a given nucleus that there is a non-zero probability that it may decay at any time t is equal to 0 and even immediately. So according to the given question, it states that its half-life is 8 days. So basically half-life means that the decay is 50%, is number of days is 8. So you can say the half-life means 50% of nuclei decay in 8 days. And it can also be said that the individual nuclei may decay sooner or later because of this random as well as spontaneous process. So from here also we can say that individual nuclei may decay sooner or later. Because of these two processes, one is random, another one is spontaneous. So we cannot be sure that how much time a particular nuclei is going to decay. Therefore, we can say that there is no fixed time for particle nucleus to decay. Now let us check, or same thing can be also summarized by the equation also. This is a standard equation, and we know that the number of nuclei decreases exponentially. And that formula is our n is equal to n naught e raised to power minus lambda t. So entire decay process is based on this particular equation, and it states that it decreases exponentially. So rate of exponential decay, we can just draw an approximate figure. So rate of exponential decay, it can be something like this, or it can be also like this. So there is no fix how it is going to decay. Okay. So therefore, if you check the options that are given to us, the option number D suits the entire description, which states that a given nucleus may decay at any time after time t is equal to 0, and which basically means that this decay can be a little bit faster, like this also. So as soon as it is greater than 0, the decay can be of any type. We can say option D is correct. Next question. It was asked in the year 1998, and it states that X-rays are produced in an X-ray tube operating at a given accelerating voltage. The wavelength of the continuous X-rays has the value from. Okay, so we have to find out the wavelength, and this is based on actually we call that as a continuous X-ray spectrum. It is called as a continuous X-ray spectrum, and there is a technical term associated with it. It is called the Bremsstrahlung long. It is a little bit typical. Bremsstrahlung long. This is BREM double S TRAHLUNG. This is the technical term, which is also called as a continuous X-ray spectrum, and it states that whenever the high energy electron strikes a metal target, they decelerate rapidly, and which produces a continuous X-ray radiation. You can say that when a high energy electrons strike a metal target, they decelerate they decelerate rapidly, decrease rapidly and produce continuous X-ray radiation. Continuous X-ray radiation. And here the maximum energy can be related with when all the kinetic energy of electron is converted into a single photon. And we can say that the maximum energy corresponds to when all the kinetic energy of the electrons is converted into single photon. Single photon. And this particular photon is now going to have the minimum possible wavelength. This single photon will have minimum possible wavelength. Or we can say lambda minimum will be equal to Hc upon E times the voltage. So therefore we can say that the wavelength is going to vary from lambda minimum to a highest value of infinity. So therefore we have a wavelength range from lambda minimum up till infinity. So the option that is correct is option number B. B is correct. And this can be also described with the help of a graphical situation also. So this is a lambda and we have this as energy and its curve is something like this. So this point is our lambda minimum. Okay, so it varies from a minimum value of lambda up till infinity. Next question. It was asked in the year 1999 and it states that photoelectrons are emitted when 400 nanometer radiation is incident on a surface of work function 1.9 electron volt. These photoelectrons pass through a region of containing alpha particle. A maximum energy electron combines with an alpha particle to form He positive ion, emitting a single photon in this process. He positive ions thus formed are in their fourth excited state. Find the energies in electron volt of the photon lying in the 2 to 4 electron volt range that are likely to be emitted during and after the combination, taking H as 4.4 into 10 to the power 15 electron volt second. So here we have to find out the energies of the photon which is going to lie in this particular range, that is 2 to 4 electron volt range. And the electron that is being emitted combines with your alpha particle, and it is going to form a He positive ion. Okay, alpha particle is basically He2 positive, and with the combination of electron we are getting a result of He1 positive, and in this process a single photon is being released. This is the basic premise of the question. So first of all, we are going to find out the energy of the incident photon. Energy of incident photon, and let us call this as E photon, which will be equal to, in terms of electron volt, this will be our, normally the formula is Hc upon lambda, and in terms of our electron volt we can write this as 1240 upon lambda. Lambda is given as 400 nanometer, and this gives us energy of photon is our 3.1 electron volt. So based on this we can easily find out the maximum kinetic energy of a photoelectron. Maximum kinetic energy of photoelectron, that is our K max, will be equal to energy of the photon and minus the work function. So we get our K max will be equal to energy of photon is our 3.1, work function is given to us as 1.9. This gives us that the maximum kinetic energy of the photoelectron will be equal to 1.2 electron volt. Now this particular electron will be captured by the alpha particle. So you can say that electron captured by alpha particle, electron captured by alpha particle, and this result, the combination, this result in the formation of our He positive and giving us a atomic number of 2, and this is nothing but our you can say hydrogen like atom, forms H like ion. So therefore we can say the energy level for hydrogen like atom energy level of hydrogen like atom formula is quite straightforward. For the nth level it will be equal to minus 13.6 z square upon n square. Value of z is over 2, so we get our E of n will be equal to minus 13.6 multiplied by this comes as 4, and we have our n square, giving us that for the nth orbit, nth of our state, it will be equal to minus 54.4 divided by n square, and this is in electron volt. And the kinetic energy that is associated with the electron is 1.2 electron. So it means the final bound energy must be at least minus 1.2 electron volt. So we can say that electron starts with kinetic energy that is 1.2 electron volt. So its final bound energy must be minus 1.2 electron volt. So substituting this in our this for nth, and we can write that our minus 1.2 is equal to minus 54.4 n square, and this gives us that our n square will be equal to 54.4 divided by 1.2, and this gives us that our n is approximately equal to 7. And it states that we already know that the ground state is given as n is equal to 1, and it's mentioned in the question that the excited state is 4th excited state. So it means the value of n will be equal to 5 for the excited state. So we know that ground state is our value of n is equal to 1, and 4th excited state gives us that the value of n is equal to 5. So it means the electron lands in n is equal to 5. Therefore, electron lands in n is equal to 5. So now we can easily find out the photon transition from n is equal to 5 to n is equal to the lower level, which is our n1 or n2. You can see photon transition from n is equal to 5, and the relationship is E is equal to 54.4, and we have this as 1 upon n1 square minus 1 upon n2 square, and this energy is in electron volt. And we are going to compute this transition starting from n is equal to 5 in the downward direction. Okay. And because it is also said that the range should be 2 to 4 electron volt range. Okay. So we start from our 5 and end at 3. So we get our energy is equal to 54.4, and we have this as 1 upon 9 minus 1 upon 25. This gives us 3.8 869 electron volt, and we have to find out it in the range of 2 to 4 electron volt range. So next is our from 4 to 3, we can say our E is equal to 54.4, and we have 1/9 minus 1/16. This gives us 2.644 electron volt. And if we want to do further calculation, we can also calculate like 5 to 4, 5 to 2, 5 to 1, then 4 to 2, 4 to 1, and 3 to 2. All these will be out of the range. So these are the only correct options. This is within the range, and this is also within the range. And same formula, if you want, we can just write that from 5 to 4, we get the value of energy is 1.224, and from 5 to 2, we get value of energy is 11.424, and from 5 to 1, we get value of energy will be equal to 52.224, and all these are electron volts. Okay, so this entire spectrum, let me write, this is our 4 to 2, and we have our 4 to 1, then we have our 3 to 2, and we have our 3 to 1, and lastly we are having 2 to 1. All these are outside the given range, outside the range. Range is basically between 2 and 4. Next question. It was asked in the year 1999, and it states that the half-life period of a radioactive element X is same as the mean lifetime of another radioactive element Y. Initially, both of them have the same number of atoms. Then we have to find out what will the relationship between the decay rate of X as well as Y. Okay. And in this case, the important part is that the half-life period of X is equal to mean half-life period of Y. Okay. So we can say that half-life of X is equal to mean lifetime of Y, or in simpler terms we can write this as our half-life, let us suppose X is called a T of X, is equal to mean, that is our tau of Y. And we know the relationship between the mean life as well as half-life. Relation between half-life and mean life, and that relationship is our tau is equal to our half-life divided by natural log of 2. We can be approximately written as half-life, and this is about 0.693. And now we can just modify this equation according to the given question. It says that Tx is equal to tau y, so therefore we can write this as our so we can write that for having t of x is equal to tau of y, we get t of x is equal to t half of the y divided by natural log of 2. And from here we can write that the half-life of our y is equal to natural log of 2 multiplied by half-life of our x. And natural log of 2, this can be written as 0.693 times tx. And obviously this particular term is less than our tx. And we have to keep in mind that in this particular case the half-life of x is directly taken as t of x, okay, whereas for our y we have written is t half of y. Now in terms of our decay constant, we know that our decay constant lambda is equal to 1 upon tau. So we have two x and y, so we can write our lambda of x can be written as natural log of 2, and we have half-life of x, and we can write our lambda of y is equal to 1 upon tau y, and this gives us 1 upon tx. So their ratio, we can write that our lambda x upon lambda y will be equal to natural log of 2, and which is approximately equal to 0.693, which is our less than 1. So therefore we can write our lambda of y is greater than our lambda of x. That's the decay constant of y is greater than decay constant of x. So therefore element y decays faster than x. Faster than x. And so y decays faster than x, so option C is correct. And in terms of initial decay rate, because option A is in terms of initial decay rate, so we can just also find out. So we can say initial decay rate and initially it is said that both are having same number of atoms. Initially they are at the same quantity. Okay, so we can assume that initial number of atoms in both cases, let us suppose it is n naught. So therefore we can write that our decay rate, which is our r, can be written as lambda times n naught. That is a general formula. And we have two elements, so similarly we can write our decay rate for x will be equal to lambda x times n naught, and lambda x is our natural log of 2 divided by tx and multiply over n naught. and we can write our decay rate of y is equal to lambda y n naught, which is equal to 1 upon Tx times n naught. So we can just find out our r of y in terms of Rx. So we can write that our r of y is equal to r of x multiplied by 1 upon natural log of 2. Natural log of 2 we already know is our 0.693. So therefore this gives us that our r of y is greater than our r of x. So they don't have the same decay rate initially. So option B, A, B and D are incorrect. Only option C is correct. Next question. It states that a particle of mass m at rest decay into two particles of masses m1 and m2 having non-zero velocities. The ratio of their de Broglie wavelength of the particle lambda 1 and lambda 2 is. So here we are going to use the conservation of law, and it says that initially the original particle, which is of mass capital M, is at rest. Okay. So we can say that conservation of law and states that the original particle is at rest, and which basically means that our initial momentum should be equal to final momentum and initial momentum is equal to 0, or we can say our total momentum is equal to 0. Therefore we can write that our P1 plus P2 is equal to 0, or we can say our P1 is equal to minus of P2, or in terms of magnitude we can assume that P1 is equal to P2 is equal to P. So which also we can say that both are with equal momentum but in opposite direction. And the de Broglie wavelength which is our lambda is equal to h upon p. So based on two particles, two wavelengths, lambda h1 lambda 1 upon h upon p1, and we have our lambda 2 is equal to h upon p2, but p1 is equal to p2, h is equal to h. So this gives us that the lambda 1 is equal to lambda 2. From here we can say their ratio is equal to 1. So option C is correct. Next question. We are given the order of the magnitude of density of uranium nucleus is MP. 1.67 into 10 to the power minus 27 kg. Oh, we have to find out order of mass of proton is given to us. And from here, from the mass of proton, we can easily find out the mass of nucleus, uranium nucleus. And you can say mass of uranium nucleus that is our capital M is equal to A multiplied by mass of proton. So we get this mass is equal to 238, that is our value of A, multiplied by 1.67 into 10 to the power minus 27, and this comes approximately equal to 4 into 10 to the power minus 25 kg. And we have to find out its density, and the radius. So we can say radius of uranium nucleus, radius of uranium nucleus that is our R will be equal to 1.2 into 10 to the power minus 15 multiplied by our 238, and it's 1 by 3. So we get that our R is approximately equal to 7.44 into 10 to the power minus 15 meters. Now we can find out the volume, and from there we are going to find out its density. So we can say volume V is equal to 4 by 3 pi r cube, which gives us 4 by 3 pi r, and this comes as 7.44 into 10 to the power minus 15 whole cube. So we get our volume V is approximately equal to 1.73 into 10 to the power minus 42 meter cube. Now we come to the finally the density. Density rho will be equal to mass oblique volume, and mass we found out is our 4 into 10 to the power minus 25, and volume is our 1.73 into 10 to the power minus 42. This comes as approximately equal to 2.3 into 10 to the power 17. So the order it is asked, that is 10 to the power 17. So option B is correct. Next question. It is said that 22e any nucleus after observing energy decays into 2 alpha particles and an unknown nucleus. The unknown nucleus is, so the atomic number is given before decay, that is our 22, and here we can just use the conservation. Okay, so we can say conservation of nucleon number and charge. And we are given before decay we have a atomic number of 22 and total charge. So before decay the atomic number is 22 and total charge that is the value of Z is 10. And after decay it says that 2 alpha particles and so we are going to have each having an atomic number of 4 and for Z is equal to 2. So based on this we can say that our total alpha particle will be equal to 2 into 4, that is our 8, and our Z total will be equal to 2 into 2 is equal to 4. And for unknown nucleus let us suppose we have our A of u and Z of u. So simply conservation we can write that our A of u plus 8 should be equal to 22. This gives us A of u is equal to 14 and A of Z, sorry, not A of Z but Z of u. Z of u plus 4 should be equal to 10. This gives us that of Z of u is equal to 6 and here is 14. So this is basically nothing but our carbon, C614. So option B is correct. Is correct. So this completes the 11 questions from the year 1998 as well as 1999. So total question were 11. This completes all these 11 questions. Thank you.